the chat window. The chat window is open. I will repeat your question and then I'll try to answer it. So without further ado, it's a bit of a recycled talk, so I hope you don't mind too much, but I hope you can still pick up some new information. So, as it's recycled talk, there's a quick thing about SIB and about Switzerland. Switzerland is a country that cannot even standardize on its languages, can standardize on the fact that trains should arrive on time, and that collaboration is a federal affair, but many things are locally in the canton. Very similar in the SIB. You have lots of collaboration, lots of groups working together. We can all agree that we need to write papers and that we like to do things, but there's no major top-down management which says we all have to use the same technology. That wouldn't work in the way that we are operating and organized. Still, at the same time, we have connections between our databases. We don't just share co-authorship in our papers, but we actually have some of our databases that interoperate. This requires a social coordination, not just a technical feature. It's an intentional desire to do better for the scientists which use it. And that is because we try to be fair. And if you haven't heard of FAIR, you haven't written a bioinformatics grant or read a paper in the last few years. FAIR is not just a buzzword. There's lots of technical things why FAIR is actually something we can do. It's not just to make sure that we win our buzzword bingo. So making yourselves interoperable, making our data reusable, well, making our data reusable already assumes following standards, and then preventing our data to make it accessible. And for many pragmatic reasons, we try to use RDF technologies. So what the heck is all this RDF about? Now, look at the classical bioinformatics pipeline. You have a parser, you write another parser, you write some more parsers, you make some database schemas, and you load it into your database so you can query it. Just some examples, pragmatically. The Go ontology would give you OBO files. UniProt might give you XML, flat file, these days JSON files. You have your own data, which might be in Excel or in any kind of other format. So you would parse it, standardize it, build an ETL pipeline, an extract, transform, load the pipeline, and load it in your database. Technically, these are all straightforward things. We've all done this. We've all written parsers at some point. We've already made a little bit database schema, and we've loaded into our databases, small or big. But each of these steps costs money and doesn't change if we use MongoDB or Solr or Oracle. All of the fact that we just have to do a certain amount of work costs. Now in the RDF world, it's slightly different. Go will be in GoAL, which is an RDF serialization with some extra features. UniProt will give you RDF XML or turtle files. Your database might give you some JSON-LD, HTT, but all of these would be RDF. And because RDF embeds its schema in its representation, when you're developing it yourself, you would only have to make your own schema. You don't have to redo the UniProt schema. And we at UniProt don't really need to do the Go schema or the Rhea schema. So you still have to load it in your database. So it still costs something. But because we have federated querying, if you are actually wanting to interoperate with large databases in the RDF world, you don't actually need to load the big databases. If you want to interoperate with UniProt, you can federate query with UniProt. What's a federated query? It's basically asking two databases to pretend as if you are one database, or three databases as if they're one database. So you're still responsible for your own schema and your own database, but you're no longer responsible for ingesting all of UniProt, all of the gene ontology, plus all these other existing SPARQL endpoints into your own infrastructure. So big savings in time and effort, especially for the analytics. How is this possible? Well, because we solve a very important problem. What is 9993? Go to one of our major collaborator competitors in the US, NCBI. What is 9993 according to the NCBI? It's many things. It's a taxon, it's a paper, it's a gene, and depending on where you are, you might get completely different answers. And you might think, well, that's not so important in practice, but I have seen people joining, well, the PubMed table instead of the gene table by accident, and of course getting complete nonsense in the results, just because they reused identifier. To be able to have identifiers that are actually pragmatic and allows this fair interoperability and this kind of co-organized databases, we need to make sure that we disambiguate, that we don't say 9983 is, well, sometimes it's a marmot and sometimes it's a paper. Well, how do we do that? IRIs. An IRI, an IRL, URI, they're the same kind of things, substandards besides. It basically allows us to say, this 9993 is a taxonomy. This 9993 is NCBI gene. And this 9993 is the PubMed. This allows us to very much disambiguate what exactly we're talking about. And then when we ingest some data, we don't need to say, oh, this 9993 needs to be separated from other 9993s because it's something else. No, the IRI already presents it. The nice thing about these IRIs, in this case, is that they're also all URLs. They'll give you a web page about the thing that we're talking about. So if you copy those IRIs into your web browser, you will actually get to the page to discuss the item. Use this concept of IRIs to identify everything. Like I said, IRIs, they're really URIs, just a slightly newer standard because they allow Chinese characters and other things in the string. A URL is also an IRI. It just happens to give you a web page. You also have IRIs which don't give you a web page, but might give you something like a book, like ISBN:9993 will give you a book. Still, IRIs are not everything. You have to end up at some point where you actually talk to humans and humans read language. So we have literals. These things consist of something like strings, but also language tagged strings. So chain in French, with a little add French, it says this is a chain. This string is written in the French language. You also have booleans, true, false, integers 1, 0, 2, decimals, which are XSD decimals, so standard float behavior applies, concepts of years, dates, date times. Something that is very unique to RDF is the concept of blank nodes. These are basically placeholder identifiers. You can imagine that you're playing a game, Find the Murderer, Cluedo, and you're getting, you know there's a murderer, you just don't know who. That's the point of the game, to figure out who's it. Mostly it's the butler. So you would say, well, I know that the murderer suspect is tall and has brown hair. And during the game, you will reason about it. And at some point, you will say, aha, it is the butler who killed everybody. In RDF worlds, you also have tools which use this, like reasoners, OWL reasoners, which help you figuring out the clues. But it is also very important for us as scientists to sometimes say, well, we know there's a causative gene for this disease. We just don't know which gene it is yet. We know that it does this, it has this behavior. It might know that it's this long and it's in these kind of organisms, but which one it is, it doesn't. So these B nodes, blank nodes, allow us to give us a temporary placeholder where we can attach information. Now these things then are combined in triples. These are just very small sentences. They're also known as statements. You have subject, predicate, object. Subject is the thing we're talking about. The predicate is the relationship. And the object is then the second thing we'll talk about. I'll give you some examples. So, I love chocolate. It's a very simple sentence. I, subject, I like talking about myself. Predicate, love. Chocolate, object, where nobody complains about being objectified in the chocolate story. And then we replace each of these with an IRI. So in my case, you can use the SIP people webpage, say, oh, that's Jerven Bolleman in his role as an employee of the SIP. Even in that role, he really loves, according to the dictionary.com definition of love, a Wikidata IRI, which is for chocolate. These little sentences can be bound together. Just like a book starts with a single sentence and just combines a few million of them to write a really nice story, so does our data. We connect these sentences every time we will use any IRI to connect the graph. So the first sentence would be, I love chocolate. And then the second sentence would be, because the chocolate IRI will be reused, chocolate is an agricultural good. Chocolate makes you fat. That makes you a little bit of a graph. Chocolate gives you all acne, makes a bigger graph. And from acne, you would go acne is a disease, and so you would spread out. Just because we reuse these IRIs, we get an automatic graph behavior. And it's these global identifiers, together with the semantic standards, that make this data integration on the fly possible. What does this look like in our real field? Well, here we have some very simple RDF format called N triples. It's the most verbose and the most direct representation of these subjects. So we have an UniProt entry, P0507, which is reviewed true. Type Interoperable protein. And you might say, well, that's not very human readable. It's true. This is human readable. Not many humans read it, but some professors can read it. Mostly it looks like the code I wrote yesterday when thinking I was super smart. And lots more people can read this. Trump might disagree that this is the right person's. Many PhD students can read this one. Languages and user interfaces are human readable when somebody teaches to you, or when it looks similar enough to things you have seen before. Still, the turtle, the RDF that we are going to show, is much more readable because it introduces a lot of very abbreviations. Abbreviations are declared with a prefix. So you would have something like prefix RDF, which says, anytime you see RDF colon at the beginning of a word, well, cut and place, replace it with this very long IRI. Make a longer IRI. Base is a special prefix, which basically says the things between angle brackets, which you cannot determine to be an IRI, prepend the base to it. Data types will also have the prefixes. This is easier to read, and nicely, later on, you'll see it goes directly to SPARQL. Differences between things like JSON and flat files is there's different formats for the same data. There's no practical information loss. It's all the same triples. It's just which technology fits you better. And sometimes it's a different one. So UniProt provides the data as RDF XML because it's the oldest standard. It's been around the longest. Also, it closes the tags, so you know that the stream has ended. JSON-LD can be used to map from JSON. It's very popular for things like schema.org, where you basically embed a little JSON-LD fragment in your page and says, this page is about a sushi shop. It opens at 9 o'clock. It has sushis. RDFA, used for the same kind of reason as well, made popular by the Facebook Graph Protocol. All of them provide the same information. Other times you just say, well, I need to archive some previous research work, and I'm just going to put it on FTP or Amazon S3 buckets, and I want to have it as cheap as possible, but it'd be really nice if I can still query it. Well, then use something like HDT, which is a compressed but still queryable format. The nice thing is, other than some exotic exemptions, these formats are transferable. And when I talk about exotic exceptions, it's things like you cannot have the ASCII character for making your computer beep in an IRI, in RDF XML. Turtle allows this. So you end up with these very, very exceptional cases. But in the pragmatic, it's transfers. So at the SIP, we've been doing RDF for a long time. 2004, UniProt started with it, the Swissport group, and has been taken up by other resources. The linking up of this is the key. We do lots of cross-references to other databases in UniProt group and the Swissport group for the UniProt database. And we have been doing that has been done since Swissport was released, and other databases as well. The concept of XREF cross-reference is very important. So how come that it's taken so long for real pickup? Well, 2004 was a long time ago, I agree. There wasn't a real standard for that made it super easy to use until 2014. This is when SPARQL came with federated querying, and I'll talk about that later. Nice thing about it all is we identify all the things. In our other representations, we will have identifiers for the records, but we wouldn't have identifiers for some of the annotations. So you would be saying things like, well, in the record A, find the second annotation and do something there. In the RDF world, we actually strategically identify all these annotations. So you say directly go to that annotation and there's an identifier for it. And this is true for BG, NextProt, and other databases in the SIP who provides this data. So it was already nice that we can represent this data, but we need to query it to answer the questions, right? That's why we're hosting the data, so people can use it. So we use a query language for that called SPARQL. It's a W3C standard and has a lot of different implementations. This is just a subset of them because I had to redo the slide. So you'll have things like AWS Neptune, Stardog, Gina, which is an RDF4J, which are Apache and Eclipse Java projects. Merck has a project called Hanley. MarkLogic is a key value extra store. RDF Lib, Apache Rhea. Oracle has three implementation. Many of us use Virtuoso Open Link software, but it's not the only one. Inside the Institute, we have a variety of implementations. So this is again different from, let's say, MongoDB. There is one MongoDB implementation. If MongoDB doesn't work for you, well, good luck. You have to rewrite everything. In a federation, in the SPARQL world, it is like, well, Oracle didn't work for you. Have you tried Virtuoso? Oh, no, it didn't work for you. Neptune, MarkLogic. Maybe you want to build something yourself, RDF4J, like Merck did, Apache. So each time, because these are quite well good at implementing the standards, this is a little example that we showed. Since 1.1, it looks like SPARQL 1.1. So it has bases, it has prefixes. We just add selects, variables, and where clauses. Now, go back to our turtle example. We have a base, a prefix. We still start with our UniProt entry, P0567. A for human, it's just a favorite. It's still a SwissProt entry, and it was entered in SwissProt a long time ago already. So we replace the P0567 and we introduce a variable. Variables start with a question mark, or if you're more Perl or money orientated, a dollar symbol. You can mix and match them both in the same queries. Then we add a select, which is basically say which variable are we interested in. The asterisk is to say, give me all the variables I declared, it's shorthand. Or you can say question mark protein, because even if I have other variables, I actually only want the protein one in the output. Then we add a where clause, curly brackets close. And that is your first SPARQL query. You took your turtle data and you just changed it like that. There's 4 query kinds in SPARQL. Select gives you a nice table, which is returned in either JSON or in XML format per standards. And many people will offer CSV, tab separated, Excel downloads as well. It's very easy because the SPARQL queries go over HTTP, so they're all IRIs. When you build a query and it says this is the endpoint, you immediately get back some JSON, so it's very nice to build some small JavaScript applets, not applets, web components with it. Well, it's nice to get tables back, but sometimes you just want another graph or new triples, so then use construct. This gives more RDF, and this come back normally in the turtle, the RDF XML formats. There's ask, which is basically you just want to know true or false, right? It's like, is there more chocolate in the fridge? Yes or no. Just give me true or false. Describe is a query which is like construct, gives you RDF, but it's not to be used in software programs. It is for human data discovery purposes only. Sometimes you get an IRI and you say to the SPARQL endpoint, describe this IRI, and we'll just give convenient to gather back triples about that IRI. So it's really easy to kind of discover like where to go in the graph. It's not meant for designing queries, because what is easy to gather as triples might differ over time and over implementations. So it's nice that you can do SPARQLs, but what is the key selling feature? It's federation. So what is federation? Now, UniProt as a database uses Rhea to annotate the catalytic activity of enzymes, but we haven't consumed it. For the full power of balanced reaction search and many other capabilities, you actually need to talk to a Rhea database. There are some pragmatic reasons why we haven't just ingested it all. And most of them drive about the fact that in the past, when UniProt has done such a thing, the funders have said, well, now that other database is part of UniProt, we no longer need to fund the other database. That then leads to a category often happening of, oh, but UniProt doesn't actually know how to run the other database or doesn't actually have the funding to do so. So the other database gets killed by being eaten by the UniProt annotation pipeline, while at the same time, UniProt no longer gets up-to-date data. So when Rhea is separate from UniProt, it really shows these are separate projects. UniProt hasn't eaten Rhea, we use it. And we can do many more things because Rhea exists. So let's look at the query, for example. If you don't see the service clause, that's this little word service, and that it says SPARQL readb.org SPARQL, and then the curly brackets, then it would look as if it was one of these queries that you had before. So basically, when you go to the UniProt SPARQL endpoint and you try this one, you will actually ask the UniProt SPARQL endpoint, hey, UniProt SPARQL endpoint, could you pretend that you are hosting all of Rhea for a moment? Okay, and then ask this question to you as a combined database. This gives lots of power because now we combine these two databases on the fly, on demand. And while there's a good case to be made saying, well, UniProt could ingest all of Rhea, the R databases, or even a relatively well-funded database, can just not do this. For example, European Patent Office. It's a humongous intergovernmental organization with its own treaty considerations. UniProt is relatively well-funded, but we can't just not afford to ingest this kind of data into our endpoint. And the EPO just doesn't care enough about UniProt to do it ever the other way around. So here we do federation. You query data as the data source, which is very well funded, well beyond the day-to-day life science resources. Biomart was never going to be able to have this capability. You can still see that we have some weaknesses in the modeling and the fact that we don't reuse European Patent Office IRIs for patents, mostly because historical reasons. Still, with a little bit of data mangling, we can build the right kind of identifier, and then we can actually do the right querying for patents which are described, or patent applications to be honest, are described in UniProt, used to describe something in UniProt. The ones which of them have actually been granted, which will have a grant date, can we have that grant date? So we can do some kind of federated querying, which can be interesting for the legal side of pharmaceuticals. This is something that we couldn't do before. It's a real new capability. Again, it's because these two databases talk the same protocols. Still, there are many issues when federating. It's really great that we can do it. It's really great that we can actually figure out, oh, we can answer these kind of questions. Always thinking back to my first real bioinformatics project where I got paid for, which was basically integrate all the data, and then we can answer this question. And after 6 months of hard work, we integrated all the data and says, well, the data doesn't have the answer. Now we can answer the question first. Does the data answer this question? And if this answer comes back too slow, or the reliability is not too high, we can bring it in-house. But because we no longer need to write parsers and we just need to pump it into our own SPARQL endpoint, the affordability of this option is much, much higher. So instead of having a 6-month project which didn't go anywhere, poor potatoes, we ended up with the reality of today is the project would be much cheaper. And after 1 week, we know the federated query capabilities would work. If that wouldn't work, we would have to bring it in-house, it'd be another week. And then we would still have 5.5 months to do something with the data instead of the old way. Still, bugs add up. So if you have multiple federation partners, they have different implementations. We might be using Virtuoso, you might be using Oracle, or you might be using Stardog, and you have less and less, but still existing, especially on the Virtuoso side, compliance issues. You might have early drafts implemented or special features, and when you send them across the wire thinking that you were talking to the same database, you might end up with a small bug. And those add up the more partners you have. Downtime is also an issue. We might have 99% uptime, but if you have two endpoints, you both have 99% uptime, you're down to 98% uptime. The more endpoints you add, the higher it is chance of all of it not working fails. Query optimization inside the endpoints today are blind for the other endpoints. You don't really know what is best to ask. For example, between UniProt and Rhea, there's, well, a few orders of magnitude difference inside. UniProt being almost 60 billion triples and Rhea of somewhere in the millions. So changing the way that you ask your query, do you first go to Rhea or do you first go to UniProt, currently still gives you humongous differences in performance. Just because if you go from UniProt, you might be sending across 180 million IRIs for all the different proteins. Well, if you come from Rhea, you'll only send across 13,000 IRIs for reactions. Just the order between these kind of things will, of course, change if the query answers in reasonable time or not. Also, things like distance make a difference. If we use one of the SPARQL endpoints in Japan, and we're doing a single request for binding, or per row, result row, you end up with the fact that you have to set up an HTTP connection between Geneva, for example, and Tokyo. Well, that will take you 400 milliseconds. And then you do that 100 million times, and you're talking about 4 months. So even though each one of these operations is relatively quick, just because the distance is large, it's unaffordable. If that other database was in the same data center and the ping would be half a millisecond, it would still be a day. Completely different performance. Of course, the endpoints on the other side also change. The implementation change the number and the kind of triples. Their query optimizers might change the way that you think the answer should be answered, and that changes if it's fast or not fast, week to week. Still, if we have a performance issue, we can always decide to integrate all the data, if we can afford it. And if we can't afford it, we have to live with what was given. So it's all very nice that we have these SPARQL endpoints, but can you do something yourself? Implement your own? Yes, it's not much work. You know, you have SAM and you have BAM and GRAM and all my data is too big. Bloody genes, DNA sequencers, can you just stop for a bit? Yeah, that is for many people a problem, especially because they're currently not using SPARQL or RDF-based technologies. So what you really want is SPARQL-based views on their existing data, especially on their existing disks usage. This is possible because actually implementing your own SPARQL endpoint due to the power of open source software is not a lot of work, because in languages of Python, Java, Ruby, JavaScript, you will find there is actually already JavaScript, a SPARQL engine that you can use. And to use it, you have to implement only one single method. And that is called triples, or get statements in Java, or the query in Ruby. Get statements is typical example, which works a little bit nicer than other ones because it's typed. So get statements, you basically pass in a subject, a predicate, an object. And if one of these is null, it's a variable that will be filled out later. In Python, you use an unnamed tuple, but it's the same concept. So if you implement these kind of things, you can actually use them to wrap an existing piece of software. On the other hand, you might say, well, my data is already in a relational database. Well, there's something called R2ML, which is a standard to describe how a SPARQL query should be translated in a SQL query. It's like a dictionary to translate between a SPARQL word and a SQL word. BG Lite is a BG SPARQL endpoint, uses this. So you have open source solutions like OnTop, but you also have commercial solutions from Oracle and many, many more. It just allows you to use data in the system that you already have and expose a new API, much like some of the wizards that you would get from other tools to just give GraphQL kind of languages. So the first example of like, can you implement your own SPARQL endpoints? Yes, you can do that. This is the an example where I used Aji. Aji is one of these newfangled graph genome data models. It's written in C++. It's also sync data structures. It's mutable. It's extremely memory efficient. And it's meant to talk about today, at this moment, you actually can use variation graphs to describe DNA sequences in a population and do efficient work with it. SPARQL is the idea that, well, because we have an RG file, we can actually wrap this RG file, because it's really just a database, and introduce them a translator layer from the SPARQL using RDF-lib, the Python library for SPARQL and RDF, to pretend that these RG files are actually SPARQL databases. And all it really does is introduces IRIs for everything that is inside this RG file. So it just points directly from the Python pointer to the C++ struct and allows you to query it. For the moment, it's only read-only, but still already in use. You might think, oh, that must be a humongous amount of code. Actually, it isn't. It is 572 lines of Python. It supports all of SPARQL 1.1. It allows federated querying, and it doesn't require extra data storage. At the same time, it has both a linear view and a graph view in the same data model. This is actually quite different from RG itself, because RG will only give you the graph view. SPARQL will pretend that it is the classical linear view of sequences. So it's a bit like a multiple sequence alignment blown up. Writing these 570 lines of Python is required because, well, RG assumes a lot of code for the C++ world. Even if you just write Python code to deal with RG, you will end up with some of these things as issues. That being by some things like RG will assume internal iterators. That is basically because of C++ memory management reasons, you pass in a function inside RG. That RG will iterate over all its data and call the function against everything. Well, for the Python world, you would want it the other way around. You will iterate over all the data in RG, and you will use it and pass it into your own functions. So to deal with these kind of mismatches between the Python and C++ world, you end up with quite a lot of code. Other code is just for optimization reasons. The entire reason of RG existing is that it is supposed to be extremely memory safe. If you then wrap everything by a Python object, well, you're blowing up your memory a factor of 10,000. So you have to have quite a bit of code to be able to still use all these complementations. But the basic idea of, oh, I need to implement this one triples method, and then I'm set, that actually was not a lot of work. So that you can do for simple data formats and many, many less lines. It's already used. We actually use it in our COVID SPARQL endpoint. So we have more than 1,300 SARS-CoV-2 genomes in there. We added the annotations from INSDEC, so GenBank INA, from the DDBJ to RDF converter. We added the UniProt proteins and the human interactants on that side. NextProt also has some of the interactant data plus some extra data. BG will give you, well, where are these human proteins actually expressed? Rhea will give some extra reactions that weren't yet in UniProt and Rhea in the public releases. So these are pre-release data. OMA, which I unfortunately forgot to add to the slide, will give you what are the orthologs. The nice thing is this, it integrated quite a few COVID resources from the entire SIB in a single SPARQL endpoint, mostly because that will give both query performance benefits and the early release data that we have from UniProt. Styled it, talked to everybody. We spent about a week of work on it. I think everybody included, so that is from Severin, who did the page styling, to Tarcisio, who gave me quite a lot of the data, and Lydie Lane. I think all over the SIB, we really could say that cost us 1 week of work. I think compared to all of our competitors who are also doing these kind of integrated databases, he has spent a lot more time and these have less data, unless something like they have legal rights to more data, like with the GISAID issue. Here, the 1300 SPARQL SARS genomes are the ones which were full length and deposited in GenBank. The ones which are not deposited in GenBank, we do not have. Still, it's nice that we already have quite a few SPARQL data resources in the SIP, but it can always be more. So join us. And when you do, remember these kind of things. 1 IRI per resource. If the IRI is somebody else's resource, for example, if using an UniProt identifier, try to use the UniProt identifier, and we will try to use your identifier. One thing, one identifier is the ID. Don't worry so much about the format. If you like JSON LD because you think it's great, use it. If RDF XML is easy to use because you can use this XLT to translate what you already have, great. If you have an relational database, R2ML, excellent. Do try to reuse each other's schemas. It just makes the cost of going from one dataset to another dataset much lower. But only do so after understanding what the heck is the data that I have. I've seen some projects where you try to use RDF-like technologies and try to reuse other people's ontologies, and it kind of didn't go anywhere because there was nothing to reuse, or the reused things that sounded similar but were not quite right, and you didn't really play enough with your own data. So I hope that was interesting. Of course, in the SwissProt group, we have lots of people provide great data. There is the UniProt SPARQL endpoint, which is run by us, the Rhea one, and soon the Swiss Lipids one as well. Hamap as a database is actually a little bit different. It's actually a database of SPARQL queries that you can use to annotate your entire genome, or proteome, to be honest. So all of this data wouldn't be SPARQable if we didn't have a great team of curation and content people to actually give us the data that we can write cool queries about. And there's a humongous amount of work which goes into pipelines to actually develop and update all this data every single month. Question from Alexander Kanitz: is there a mathematical proof that all relationships can be captured in triples? Yes, there is. And there's a lot of logicians working on these kind of things. So the question is not can they be captured in triples, it's in how many triples do you need to capture it. There is the issue basically is that the predicate in between, you have a subject and an object, the predicate can be seen as a function, and the function has to be described, and just the fact that you have that and your alphabet means you can attach any relationship meaning to one of these. So as long as you can name the relationship, you can capture it in triples. It's a rhetorical question, but pragmatically, yes. Hypergraphs are allowed all these kind of things. Continuous values, let's say gene expression. Yes, they are again presentable in triples, and like all time series, they will tend to be quite expensive in modeling. Like the number of triples you get for things like lists is quite large, but that is just the materialization. If you actually store them, you can store them very, very compressed in many different ways. The very simple thing like a genome is a continuous series of values as well, right? You have ACTG about that as well. How do I find the federated databases? Basically any SPARQL database you can federate with, and just how much effort it takes the changes. Wikidata has a very nice list of SPARQL endpoints, so you can query that. And there's something called yummydata.org, and let me just tell you that, type you that in, which is more appropriate for us. Yummydata. This basically goes to different SPARQL endpoints in the life sciences and tries to see how tasty they are by giving a different quality score. Given that kind of list, you will have to investigate each one at one by one to see if they have something of value, much like you would have to do for any kind of resource in the field, which we have some ideas about to make that better. But in the end, just because you know the shape of the data doesn't mean that it's valuable data for you. Yes, so the question is, Uh, so the price question first. Yes, you can always get the relationships, so the predicates in an order that connect to subjects directly or transitively. If you want to transitively, it's a little bit longer queries, but yes, this is possible. Um, Basically, the predicate is also allowed to be a variable, completely empty. Is there a list of metadatabases that you can query to find the right one? Other than Wikidata, which is somewhat a metadata DB, no. I don't think there is anybody who has done that. So yes, there's progress in scalability of federated queries, and for SIP in particular, you have something called FedEx, so which is from the RDF4J project, and that tries to give a bit of a unified view on multiple databases that you federate. So this is not so much the ad hoc federation where you can basically decide as a querier who you're going to federate with. It requires a bit of setup as a central endpoint to say this endpoint, let's say the SIP SPARQL endpoint, pretends that it actually consumed all of the SIP independent resources, while the SIP independent resources will still be doing their monthly updates. Um, so there's big performance benefits for some query types there, but somebody needs to set it up and maintain it as well. The second one is federated querying still fails a lot because simple implementation choices by the vendors where nobody really had time to improve it. For example, you might have you might have on the UniProt side, let's say, 1,000,000 results, and it will federate with Rhea. And currently, it will send a single HTTP request from UniProt to Rhea for every binding. So it will send 180 million HTTP requests. Just the HTTP cost is quite humongous. And that could be much cheaper if instead of sending a HTTP request per binding, it would group them a bit and send them once per 10,000 requests. And it would actually improve our query performance really a lot. Virtuoso hasn't implemented that. And there's multiple reasons why that is the case. If they did, it would be much better. How to best translate a relational database to RDF, and how to best develop a joint RDF schema for several databases. How to best translate a single relational database to RDF. If you're basically saying, well, we've invested a lot in this relational database, and we are maintaining it as a relational database, and we will allow SPARQL queries against our relational database as is, then I would say go to the R2RML route, where you can basically say this is a mapping file, and you have multiple vendors who will support it, and multiple open source projects who will take these R2RML files. And then you can basically say, have this dictionary, you have standardized tooling. Now, if you're saying, I need to dump this relational database or a subset of this relational database and keep lots of things secret, so I want to have very, very controlled export, then either some custom code, because that's sometimes quite pragmatic, or a minified R2RML mapping where you then run some construct queries against is another approach, so that you can actually share the RDF data where you cleaned it and anonymized it. Develop a joint RDF schema for several databases the same way as you develop any joint thing, and that is by joiningly talking to each other and developing with experimentation a schema over time. This is really the social aspect of how to work together, especially when the several databases don't actually have a shared schema to start with, or a very disjoint schema in many ways. So then you basically do have to sit down and say, okay, I have this piece of information. Where do you store the same piece of information? How do we link this piece of information to the next step? And that is a lot of work. And that is really almost technologically independent. If you actually went to any kind of other technology, just even if they are the same technology, you might end up with a humongous implementation in mismatch. There's many Oracle databases around in the world, And many of them have schemas which are completely not mappable to each other without serious amounts of effort. Do you suggest RDF1, RDFA? RDFA is RDF that you embed in HTML web pages. For UniProt.org, I've decided to use RDFA for some very scalability-oriented reasons and search engine optimization reasons. So the RDFA that is embedded in UniProt.org web pages is schema.org style modeling of the data, which is somewhat different from how the RDF for analytical queries needs to be structured. This is because schema.org is supported by Google search. And the reason we have web pages is so that people can find them, look things up, and many people use Google search. And we want to rank highly in Google search so that they go to us and not to our competitors. So we use RDFA inside web pages because the alternative there is JSON-LD. It's the only other thing that the Googlebot consumes. And that would increase either the size of our web pages by almost double them, because if we use an JSON-LD representation, we would have to repeat most of the information that is already in the HTML inside the RDF. So you might have something like an author name. You would have it once in the HTML and once in the JSON-LD. So then our web pages, which are already very big and an issue for performance on mobile phones, would get twice as large. If we separate them and basically say, well, you all don't have JSON-LD, doesn't need to be on the same page for the Googlebot, then we end up with the point that Googlebot will only do 300,000 requests per domain per month, more or less. If now for each page, the Googlebot has to do 2 requests, one for the HTML, one for the JSON-LD, our refresh rate of Google indexing would be halved. Now, Google, if they cared to, could change the behavior and crawl us every month fully, but they don't care to. And to be able to get as highest ranking as possible, for the Interoperable case, we decided to go with RDFA, which is basically embed the RDF inside the HTML by adding extra properties to the DOM. Research object crates. Yes, they tie very in much with RDF. I think they're actually mostly going via YAML to JSON-LD to RDF, and people can run SPARQL queries on them. Research objects are, I think it's not really my day-to-day cooking, is a way to describe information artifact coming out of a computational pipeline and say, okay, this was run, and this is what was done to it, and this is the results, and this is who did it, and when it was done, and this is where it's stored.
Yeah, correct. That's my understanding too.
Yeah, so that actually comes out as an RDF object. So the research object thing is the RDF object. The metadata for there is RDF representation. It might be quite hidden because it's behind the YAML, which is actually JSON-LD business. But in the end, you can use it that way, and Arvedus, I think, uses it that way. Like I said, it's not my day-to-day concept.
Yeah, sure. Thanks a lot.